Okay, so welcome back to another video. So here we have an improper integral integrated over the entire real line, and as we see, we have a bunch of the golden ratio number implemented into our integrand. We have e to the negative x plus 1 times x plus 1 over phi, and then divided by 1 plus e to the power negative phi times x, then followed with dx. So not much needs to be done aside from the fact that you can probably guess that a u-substitution will be involved. But it's actually pretty simple of an integral to evaluate than you might think, as a lot of this stuff really is more just manipulating the algebra behind our integrand. Simple as that. And of course, the last step is actually just be utilizing a special function, which it's everyone can kind of know where I'm going with this one eventually as we get through it. But not much needs to be done. It's a pretty simple integral, pretty short video for this one. In this case, I haven't done integrals in quite a while, but I figured we start off something a little simple in this aspect. So why don't we actually just jump right in? Okay, so the first thing we can do is, as you can see, we have x plus 1 divided by phi. Let's actually multiply that entire thing out. So let me just call our integral capital I. So we have negative infinity to infinity of e to the negative x squared. So multiplying all this out, I have minus x divided by phi, minus x, and then minus 1 divided by phi, and then divided by 1 plus e to the negative phi times x, and then dx. Okay, so then next thing I'll do is, you'll notice that I can actually factor out an x from these two terms over here, so that's what I'll do. And then taking another step ahead, I'm going to multiply a e to the positive phi times x to both our numerator and denominator. You'll see why we do this. So doing so e phi x, and then multiply by e to negative x squared. So then I factor out our x, so it's x, and then times 1 plus 1 divided by phi, then minus 1 divided by phi, and then all this being divided by, so e to the power phi times x, and then plus 1 followed by dx. Okay, and so we notice that specifically what's being multiplied by 1 plus 1 over 5, that's a nice little relation to say that that's actually the same thing, simply just equal to 5. If you actually just solve the equation x squared minus x minus 1 equals 0, and we actually get that solution, that's another way to actually utilize that. So with that being the case, we can actually just put in that substitution. Let me put this over here, so that's the same thing as just phi by itself. So then now this is just going to be, so we haven't really done much yet, so infinity, negative infinity, so e to the power phi times x, multiply e negative x squared, and then multiply by, or minus phi times x, and then minus 1 divided by phi, all being divided by, so e to the phi power x, and then plus 1 with dx. Okay, so now the next thing I'll do is, as we see that e to the phi x, what I'm going to do is I'm actually just going to multiply this just specifically to the terms of e associated with these two terms over here. So e to the negative x squared is going to be just left out by itself. So if we actually just perform a little bit of some multiplication, we see that e to the phi x then times e to the minus phi x minus 1 over phi. Of course, that's going to be the same thing as e to the negative 1 over phi. That is still a constant. So with that being the case, so let's see, that's so far I is going to equal to negative infinity e, so e negative phi x, or actually that's supposed to be just, my bad. That's actually supposed to be e to the negative 1 divided by phi, then times e to the negative x squared, and divided by 1 plus e to the negative, or rather positive phi x. Addition, I had a little backwards, but it's still the same thing either way. So dx. Okay, so now another thing is, let's actually factor out our constant e to the negative 1 divided by phi, multiplied by the integral from 0 to, or infinity to negative infinity to positive infinity, e negative x squared. So let me actually just fix the orientation. So I'll put this as like this. Okay, so that's what we have. And then now what we can do here is, as I mentioned, let's actually perform a little u-sub. So the u-sub that we'll be using, or what we'll be substituting, we're going to let u equals negative x. Okay, so that means du is going to equal negative dx. So therefore, in this case, if I just get dx by itself, then it means negative du is then just equal to just positive dx. Okay, so then reiterate all this. So I is then just equal to, so far, e to negative 1 divided by phi. So then we change our bounds. So this is going to be negative infinity on the top, infinity on the bottom. So e minus and then negative u square. then divided by e to the phi, and then times negative u, and then plus 1 multiplied with negative du. So we actually just fixed this up. We changed this up just a bit. So we just changed our bounds, and then that's a negative. That cancels out. So e to the negative 1 divided by phi. And then we multiplied this. Let's see. So negative infinity, infinity. Then afterwards, we're going to be left with e to the negative u squared, and then divided by, so e minus u phi times u, and then plus 1 du. And the next thing we'll do is let's actually multiply e to the positive phi u to both the numerator and denominator. So I have e with 1 phi, and then the integral negative infinity to positive infinity of e to the phi u. Oops, I accidentally wrote that first. Phi u, then times e to the negative u square, and then divided by 1 plus e to the phi u, and then du. Okay, so that's what we have. And then of course that is still set to I, and I is still considered the same thing as over here. So what if we actually just add the two integrals together? So that means they are still the same thing, so we get a double. So meaning I have 2 times I, and then what I'm going to do is I'm going to add this integral and then add this integral together. And then you'll notice that, so 2 times I is then equal to, so first I got to write the constant term over here. So e then negative 1 divided by phi. And then that's going to be multiplied from negative infinity to positive infinity. So this is 1 of this, and then plus an e to the phi u term. So if I just factor out the e to the negative x squared, since this is just dummy variable, so it's okay, we can just go back to the world of x. So I have 1 plus e to the phi times x, rather. We're just going back to x, then e to the negative x squared, and then divided by 1 plus e to the phi x, then dx. Look, we just have something that just cancels out. So that means we're just basically left with e to the negative 1 phi u, and then, or just phi, then negative infinity to infinity of e to the negative x squared. As you already can guess, we see that this is actually just the Gaussian integral over the entire real line. And then another thing I can do is just divide this by 2, even though there's really no 2 here, but consider that because that our integrand is an even function. And so we can actually just split this up a little easily to say that I is then the same thing as e to the negative 1 divided by phi, then from 0 to infinity of e to the negative x squared, then dx. And we know that if you actually, several ways to calculate this, polar coordinates using the gamma function. This is the same thing as evaluating at gamma at 1/2. We know that that's the same thing as equal to the square root of pi divided by 2. So therefore, this is just reduced to the square root of pi divided by 2 times e to the negative 1 divided by phi. Therefore, that is our final answer to our golden, the golden ratio integral. Yet another one of, you see it, of many on this channel over here. So everything that just reduces to here. Then, yeah, I forgot to mention that crucial step that we'll be actually adding a double, but that's the surprise of anything. So yeah, that's pretty cool if you ask me.